Hello there. So, here's an example question, which I'm gonna solve. So use Green's theorem to evaluate the line integral, of f dr, where f of xy is given, as you can see right here, and C is a circle right here. It's a circle with radius 5 oriented clockwise. So it's important to note that, so I'll start solving it. So note that it's clockwise. So if we actually have a circle, it would look like this, but we're integrating over the wrong direction, as in it's negatively oriented. So whatever answer we get using Green's theorem, we're going to have to take the negative of that. So we'll keep that in mind. Alright, so what does Green's theorem actually tell us? Well, we know that the line integral of f dr over this curve C is actually equal to the double integral over A, where A is the enclosed area. So it's enclosed by the curve C. So in this case, our A is this thing right here. That is our area we're going to integrate over. And that is, so it is q of x minus p of y, the partial of x and the partial of y, dA. So what is q and p? Well, this is when f is in the form of p comma q, the x and y components. So let's look at this, that, and that. So our p is e to the x plus x squared y, and our q is given there as e to the y minus xy squared. So let's find q of x, which is the partial derivative of this with respect to x. So what is that? Let's look at the coefficient of x. It's y squared, but there's a negative sign, so that is negative y squared. What about p to the y? Similarly, we look at the coefficient of y, which is x squared. So p to the y is x squared. So now when we look at this integral again, this is equal to the double integral over the area of qx minus py, which is negative y squared minus x squared dA. And that's much easier. Oh, and there's a negative sign here. Why? Because it is oriented clockwise, and we want, by the right hand rule, it should be oriented counterclockwise to make the curl, well, forget about that. Basically, it has to be ordered, I already explained this, but you want the negative sign to compensate for like the normal being pointed downwards when you want it to be upwards. Either way, our magnitude is still going to be this integral. So what does this look like? Y squared minus x squared. Y squared and x squared. Well, first of all, we can get rid of negative signs to just make it equal to the double integral or the area of y squared plus x squared dA. Now, would we really want to do this, or as it is, using Cartesian coordinates? No, we would convert to polar. So this is the same thing as 0 to 2 pi, 0 to 5. So like that's the bounds. We'll change x and y to theta and r, where if you look at the circle, now we have some angle which is sweeping all the way here from 0 radians all the way to 2 pi radians. And at each slice of the angle, our radius is going from 0 the center to 5 in the perimeter. That explains those bounds. Now what is y squared plus x squared? Well, that is just r squared. And now we have to take into account the Jacobian, which is another factor of r. dr d theta. Alright, what is this equal to? This is equal to 0 to 2 pi of, well, we have r cubed, so we want to take r4 over 4, the integration from r equals 5 to r equals 0 d theta, which is equal to 2 pi times 5 to the 4th over 4, which, if you do the math, is equal to 625 over 2 times pi. And this is the correct answer. Thanks for watching.